In this video, we're going to take a brief look at the technique of mass spectrometry. And what it is, it's an analytical technique that's used to get the molecular weight of a compound, and then from that, we can often figure out the molecular formula. To understand basically what's happening in a mass spectrometer, we're going to start with a very simple molecule, just methane. And what happens is you put that into the instrument, it gets blasted with an electron beam, and those electrons hit this so hard that what it actually does is knocks a single electron out of the methane molecule. And when we lose an electron, it then gets a positive charge. So we get this structure right here that the notation at the top, we have the radical and a cation. This is called a radical cation, and this is methane that's had an electron removed. This species here is called the molecular ion. And it corresponds to the mass of the molecule. So the mass of methane is 16. Losing an electron is negligible in terms of mass loss. So the molecular ion, which is 16, corresponds to the weight of methane. And it's often written as this MZ term, which is just a mass to charge ratio. The molecular ion is, of course, unstable. So what it can do is then fragment into other fragment ions. So here's just one example. It fragments to lose a hydrogen atom, and then you get a carbocation, which has an MZ of 15. All of these pieces are then recorded on the mass spectrum, which we see down here. On the x-axis is the mass to charge ratio, which tells you about the molecular ion and any fragment ions. The y-axis is just the relative abundance. So generally, and this is a very simplified mass spec, but what you want to do is look at your group of peaks to the farthest right on the spectrum. And in most cases, your tallest peak in this group is going to be your molecular ion M+. So right here at 16, that's our molecular ion. And then anything with a lower mass than that would appear down here on the mass spectrum is the fragments. So we see this fragment at MZ15. It is important to note that only positively charged species are detected on by mass spec. Now you might also notice this little blip at MZ17. This is called the M+1 peak. What that is from the little bit of natural abundance of carbon-13 in any sample. So in the sample of methane, almost all of the molecules in that sample are going to contain the carbon-12 isotope. But there's going to be a small percentage of the carbon-13 isotope. It's actually 1.1%. And because there's a little bit of the carbon-13 isotope, and that extra neutron makes it one mass unit higher, we see this small peak. So in any mass spectrum, you should see your molecular ion and then a small peak for the M+1. All right, we're going to look at a few common atoms you can find in mass spec and some tips and tricks that we can use. So first, here's this mass spectrum, and when you're analyzing it, your eye should really go to this rightmost grouping of peaks. That's where your molecular ion is going to exist. The tallest one in this peak happens to be our molecular ion. This little one right here is the M+1. Now what we can see is that the molecular ion here is at 41. So we're going to look at something called the nitrogen rule, and it's just a useful way to know if you maybe have a nitrogen in your molecule. If your M plus is an odd number, that means you have an odd number of nitrogen in the molecule. So you might have 1 nitrogen, 3 nitrogen, 5 nitrogen, and so forth. If you have an even M plus, then you either don't have any nitrogen in the molecule, or you could potentially have an even number of nitrogen. So in this case, we have our MZ of 41. We know that there's at least 1 nitrogen in this molecule. So the data this particular mass spectrum gives us is whatever our unknown is, has a mass of 41, and has a nitrogen in it. Another useful thing that's easy to spot is a bromine. This is because when you have bromine, it's actually a near one-to-one mixture of 79 bromine and 81 bromine. For that reason, you're going to see peaks in the mass spectrum for both of those. So if we look at the mass spectrum of this molecule, here's this rightmost grouping of peaks. Well, we see this peak right here, which we'll say is our M plus, but now we have a little blip, we have another peak, 2 mass units higher than the first. So this is M plus 2 plus. And that corresponds to the 79 bromine isotope and the 81 bromine isotope. So if you see this particular ratio, M plus 2 plus, in a 1-to-1 ratio, that tells you you have a bromine in your molecule. Similar to the bromine, we can also detect a chlorine. And with this, the 2 isotopes of chlorine are going to be 35 and 37. But unlike bromine, they don't exist in a 1-to-1 ratio. Instead, they exist in a 3-to-1 ratio. But that's useful because that allows us to see this in the mass spec. So if you see an M plus to M plus 2 in a 3-to-1 ratio, and that's what we have here. There's M plus, here is M plus 2. 3-to-1, that indicates the presence of a chlorine. So the data that we can get out of this particular mass spec, it looks like the M plus is at 112, and we have a chlorine. So using this data, we're not going to get into exactly how to do that, but chemists can use this information or even exact masses to figure out a potential molecular formula for this compound.